a rational function. So we start with 58, and this is on page 429. Of course, we're asked to graph. We're asked to understand the function, and that's what we are doing. We understand the function, and then we graph it. So f of x equals 3x over x minus 1. Oh, I didn't share my screen. I did or I didn't? Anyone with me?
I don't think you did. It didn't share for me.
Oh, I'm so sorry. Forgive me. So I chose 58. Then I'll let you choose the next. Okay. So is this a rational function? Yes. Which type is it? Is it type 1? Is it type 2? Or is it type 3? I need to know from the beginning.
Type 2.
Type 2. Type 2 will be when the denominator has a higher degree than the numerator. So the degree of the top is 1. The degree of the denominator is 1. So this is indeed type 1. We agree? Everyone, please.
Yes, but is it because there's one x? It's just x up top and then x at the bottom in the denominator?
The degree. The degree is 1.
Okay.
And the degree is 1.
Okay, I see.
So this is a linear expression, and this is a linear expression. The linear expression has degree 1. The linear expression has degree 1. So it's degree 1 over the degree 1. That's why it's type 1. Is that okay?
Yes, thank you.
Perfect. Now, we start our table. Can anyone give us the domain of this function? That's our starting point always. I cannot build the table before I find the domain. So can anyone tell us what is the domain of this function? This is something from the past. This is not something new.
Infinity to infinity?
So what could be the problem with this function?
Rejects.
Would we take the denominator and say that x cannot equal 1?
Exactly. Please remember, we cannot divide by 0. So x cannot be 1. Everybody in agreement with that? That's how math is. We have to review and review and review and review. Do we all agree that x cannot be 1 in this function?
Yes.
Okay. So negative infinity, 0 has to be in the table, 1, and under 1, I have nothing to write. I don't have to write the domain separately. It's very clear from the table. Anything but 1. In this case, I'm going to write immediately that x equals 1 is the vertical asymptote. So when we started talking about the rational functions, we said that a rational function has a vertical asymptote when it is undefined. To be exact, I'm going to write a note. Note. A rational function has vertical asymptotes when it is undefined, unless, this is a very important situation, we're going to have examples, unless the factor that makes the function undefined simplifies. I'll give examples. Okay, I want to write one more thing here. In that case, the function, if it simplifies, the function has a hole in the graph. Okay, we don't have an example right now of this, but I cannot tell you that something is true because there are other situations in which what I'm telling you it's not true. So a rational function has a vertical asymptote only when, so in general, but if the factor, I'm going to erase this, but if I have a factor of x minus 1 here, and that simplifies, the function is still undefined at 1, but it will not have a vertical asymptote, but a hole. This is not our case right now, but I cannot mention the whole truth. Okay, so in this case, the factor of x minus 1 doesn't go anywhere. Therefore, x equals 1 will be a vertical asymptote. The factor is there. Therefore, x minus 1, x equals 1 is a vertical asymptote. Now, what did we say about the horizontal asymptote, which is also the end behavior for such a function? Let's take a look. Let me go back to the page. So it's type 1. Scroll forward. What did we say about the horizontal asymptote? How do we determine it? The leading coefficient of the top divided by the leading coefficient of the bottom. That is also the end behavior. So, what is the leading coefficient of the top?
Three.
Perfect. What is the leading coefficient of the denominator?
1.
So how much is 3 over 1? Y equals 3, horizontal asymptote. Notice that the horizontal asymptote is identical with the end behavior. For the end behavior, I did not throw it in the recycling, if you remember. This was the end behavior for polynomials, because it was a totally different story. This is the end behavior. The horizontal asymptote or slant asymptote is the end behavior of the function that is rational. Okay, can anyone plug in 0 here and tell us what we get? Because we need to find the x and y intercepts. When x is 0, what do we get? How much is f of 0?
Zero.
Exactly. 0 over -1 is 0 indeed. I need one more thing here. I know that by definition, back to the previous page, when a function, a rational function, has a vertical asymptote, it means that the function left and right of the vertical asymptote either goes to infinity, or goes to negative infinity, or goes to infinity and negative infinity, or to negative infinity and positive infinity. I know that for sure. So left and right, I will write in the table infinity. I don't know the sign. I don't know if it's positive, positive, negative, negative, positive, negative, negative, positive. This is what I don't know. Very simple. I'm not going to put those numbers here because they are only check numbers. To the left of 1, a very close number is 0.9. To the right of 1, a very close number is 1.1. I only want you, I don't need a number. I only want you to plug in 0.9 and tell me the sign of the outcome. I want you to plug in 0.1 and tell me the sign of the outcome. Just the sign. I don't care for the number. And that gives me the sign of the infinity. So notice that if I punch in here positive 0.9 or positive 1.1, this is positive. Don't even bother with it. See what the sign is when you punch in 0.9, and what will be the sign when you put in 1.1. You don't actually have to do it, just think for a moment. When you punch in 0.9, what is the sign?
Negative?
Indeed. How much is positive over negative? Now, imagine that you punch in 1.1 here and 1.1 here. I just need the sign.
Positive.
Indeed. Done. That's all I need. So now, let's graph the function. When we graph functions with asymptotes, we must graph the asymptotes first. Okay, I see two asymptotes. I see x equals 1. They're not part of the graph. And I see y equals 3. And now I read my table. Let's read the table together. The only point I have is 0, 0. From approaching 3 down to 0, down to negative infinity on the left-hand side of the asymptote. It should have been a little bit rounder. Good? We'll have plenty of examples. It may look a little bit weird at first, but you will get used to it. I wanted to get it closer a little bit rounder. Okay, I have to wait for a second. Now, on the other side, from positive infinity, getting closer and closer to 3. From positive infinity, down to 3. From 3, down to 0, further down to negative infinity on the left-hand side, and on the other side, coming from positive infinity, getting closer and closer to 3. What is this? This is f of x equals 3x over x minus 1. Yes, you can always check with the graphing calculator, but be very careful how you enter it. So the graphing calculator is not as smart as you are. It will not even know that the function has a horizontal asymptote. You have to add it as a secondary function. So the numerator, because it has only one term, it's okay not to put it in parentheses. But if you don't put the denominator in parentheses, you're not going to graph this function. I am going to use zoom standard, negative 10, 10, negative 10, 10. Here it is. Aha. So the function approaches 3 towards its negative infinity, comes down, crosses the x and y axis at the origin, and goes down to further to negative infinity. The graph will not show the vertical asymptote. You have to graph it though. And then it's coming from positive infinity, closer and closer, closer and closer to y equals 3. This is the graph of our first rational function. Now, a function will never, a rational function will never cross the vertical asymptote, but it may cross the horizontal. The horizontal asymptote is basically talking about the end behavior. But I cannot graph a line by graphing this piece and graphing this piece. I have to graph the entire line, but the function may cross the horizontal axis. I'm sorry, the horizontal asymptote, but not ever, and slant as well, but never ever, here it's undefined. It can never cross a vertical. It can cross a horizontal. It can cross a slant, but not a vertical ever. Are we ready for another example? I would like to actually give you an example like this so you understand the difference. Is that okay? Or we can leave this at the end or next time. So let's choose another problem now. But just keep in mind that if the factor disappears, there is more to the story. Okay, so we looked at 58. This was type 1, same degree over same degree. Here's type 2. 65 is type 2 because the degree in the denominator is higher than the degree of the numerator. Do we want to look at 65 or 67 or 68? So let's look at the type 2.
Can we do 67?
Yes, please. So let's look at 67. F of x equals 2 over x squared plus x minus 2. These rational functions are exciting, require a lot of work. Once you understand them, you cannot miss anything. Good. So what will be my first step? Absolutely, for sure. The answer is the domain, and I have to do something to the denominator in order to find the domain.